What if I told you that space isn't silent, that it's more like a vast, invisible ocean? And when massive objects collide in that ocean like black holes or the dead cores of giant stars, the very fabric of reality starts to ripple. These ripples race outward across the cosmos, carrying stories of events so violent that no light can escape them. For over a century, these cosmic whispers were too faint for us to hear, remaining hidden and undetectable. This is the incredible story of gravitational waves. It all started with Albert Einstein. Back in 1916, he predicted their existence, a radical idea that some physicists at the time dismissed as impossible. It took a full 100 years, but in 2016, humanity finally confirmed them in one of the most extraordinary scientific breakthroughs of our time. Think about it: a century of doubt, followed by a moment of pure discovery. Gravitational waves aren't just a new way of seeing the universe, they're a completely new sense. It's like we've suddenly gained the ability to hear the cosmos, to listen to the tremors of space-time itself. If light shows us what the universe looks like, these waves reveal what an feels like. They let us listen in on the most dramatic and secretive events in the universe's history. So, how did this radical idea go from a mind-bending theory to a proven fact? How did scientists build machines sensitive enough to detect a ripple in space-time smaller than the width of an atom? In this video, we're going to dive deep into that journey. We'll start with Einstein's brilliant mind. Travel to the massive observatories that made the discovery possible. Explore the mind-boggling mysteries they're helping us solve right now. We're talking about listening to the collisions of black holes billions of light years away. We're talking about witnessing the birth of new elements as neutron stars smash together. Maybe, just maybe, we'll even be able to hear the faint echoes of the Big Bang itself. These invisible ripples are rewriting our understanding of everything. They carry the hidden stories of the cosmos, a secret symphony that we're only just beginning to tune into. From Einstein's initial spark of genius to the incredible engineering feats of today, we'll trace the path of these gravitational waves. We'll see how they are unlocking secrets that were once locked away in total darkness. The universe has been whispering its stories for billions of years, and for the first time, we are finally able to listen. The cosmos is full of secrets, and by listening to these cosmic tremors, we're starting to uncover them, one ripple at a time. It's a new era of astronomy, and the show is just getting started. Ever wonder what it would sound like to hear the universe itself? Not through light or radio signals, but through the very fabric of reality. To understand this, we have to travel back in time into the brilliant mind of Albert Einstein. The story begins in 1905. A young patent clerk named Einstein publishes his special theory of relativity. It's a revolution, completely changing our understanding of space and time. But he wasn't done. For the next 10 years, he wrestled with an even bigger idea: gravity. For over 2 centuries, everyone accepted Isaac Newton's view of gravity. It was a mysterious force, an invisible rope pulling objects like an apple falling from a tree toward each other. Simple, elegant, and it worked. But Einstein saw something deeper, something far more bizarre and beautiful. In 1915, he unveiled his masterpiece, the general theory of relativity. And with it, he threw out Newton's invisible rope. Einstein proposed that space and time are not separate things, but are woven together into a single, flexible, four-dimensional fabric he called space-time. Imagine a giant, stretchy trampoline. Now place a bowling ball in the center. Fabric curves and dips under the weight. That's what massive objects like the sun do to space-time. They warp it. Now, roll a marble nearby. It doesn't get pulled toward the bowling ball by a mysterious force. It simply follows the curve created by the ball's mass. That, Einstein said, is gravity. It's not a force, it's geometry. It's the shape of space-time. Planets orbit the sun because they are following the straightest possible path through the curved space-time created by the sun's immense mass. This was a radical shift in thinking, a complete rewrite of the laws of the cosmos. But Einstein's equations held an even more astonishing secret. If space-time could be bent and warped, could it also move? Could it ripple? Think about that trampoline again. If you were to drop 2 bowling balls onto it, and they started circling each other, they would create waves spreading out across the fabric. Einstein realized that the same thing would happen in space. When massive objects accelerate through space-time, like two black holes spiraling into each other, or two neutron stars locked in a cosmic dance, they would create ripples in the fabric of space-time itself. In 1916, just a year after publishing his theory, Einstein predicted these ripples. Gravitational waves. He calculated that they would travel at the speed of light, carrying with them the story of their cataclysmic origins. There would be a brand new way to observe the universe, a way to listen to the most violent and energetic events the cosmos has to offer. But there was a huge catch, and it was a problem that would stump scientists for a century. The effect of these waves would be almost impossibly small. Let me put this in perspective. By the time a gravitational wave from two colliding black holes, millions of light years away, reaches Earth, the ripple is infinitesimal. It would stretch and squeeze a ruler that's a few kilometers long by a distance less than the width of a single proton. That's like measuring the distance to the nearest star with an accuracy smaller than the thickness of a human hair. This incredible weakness led to a fierce debate in the physics community. Were these gravitational waves real, physical phenomena that carried energy? Or were they just a mathematical ghost? A quirk in Einstein's complex equations with no basis in reality. The debate raged for decades. Even Einstein himself at one point had doubts, co-authoring a paper that initially claimed gravitational waves didn't exist, though he later corrected his mistake. Some physicists were adamant that detection was impossible, a fool's errand. Others, however, held on to the dream. They knew that if these waves could be detected, it would be like gaining a new sense. For all of human history, we have studied the universe by looking at light, visible light, radio waves, X-rays. It's like watching a silent movie. But gravitational waves offered the chance to finally turn on the sound. They would allow us to hear the universe. For decades, this remained a purely theoretical argument. No one had the technology to even begin to search for such a tiny signal. But then, in the 1970s, came the first tantalizing piece of evidence. It wasn't a direct detection, but something just as convincing. In 1974, two astronomers, Russell Hulse and Joseph Taylor, were using the Arecibo radio telescope to study pulsars. They stumbled upon a unique system, a binary pulsar. Two incredibly dense city-sized objects called neutron stars, locked in a tight, fast orbit around each other. This system was a perfect natural laboratory to test Einstein's theory, according to general relativity. These two orbiting neutron stars should be constantly radiating energy away in the form of gravitational waves. And if they're losing energy, their orbit should shrink. They should be spiraling closer and closer together over time. So, Hulse and Taylor began a meticulous campaign of observation. For years, they timed the pulses of radio waves coming from the pulsar, and what they found was astonishing. The timing of the pulses showed that the stars were, indeed, spiraling inward. The rate at which their orbit was decaying matched the prediction from Einstein's equations for energy loss due to gravitational waves with incredible precision too, within less than 1%. It was the smoking gun. The energy had to be going somewhere, and gravitational waves were the only explanation. The universe was whispering, and Hulse and Taylor had managed to overhear it. For this groundbreaking discovery, they were awarded the Nobel Prize in Physics in 1993. But still, no one had directly heard a gravitational wave pass through the Earth. The indirect evidence was overwhelming, but the ultimate prize, directly measuring a ripple in space-time itself, remained out of reach. For nearly 100 years after Einstein first imagined them, his cosmic ripples remained phantoms. But the dream was now more powerful than ever. The work of Hulse and Taylor proved that gravitational waves were real, and that they behaved exactly as Einstein predicted. The question was no longer if, but how. How could humanity possibly build an instrument sensitive enough to detect a distortion in reality smaller than an atomic nucleus? This monumental challenge would inspire one of the most ambitious, expensive, and daring scientific experiments ever conceived. It was a quest that would span generations of scientists and push the limits of technology, all in the hope of catching the faintest whisper from the cosmos. The stage was set for a scientific epic, the race to finally prove Einstein right and open a brand new window onto the universe. Have you ever wondered what it would sound like if the universe itself could speak? For most of human history, we've only been able to look at the cosmos, seeing it through telescopes. But what if we could listen? What if we could hear the echoes of the most violent and energetic events in existence, long after they happened, light years away? This isn't science fiction. It's the story of LIGO, an incredible machine that gave humanity a brand new sense to perceive the universe. This is the story of how we learned to hear the sound of spacetime. Our journey begins in the 1980s, with a dream that bordered on the impossible. Physicists imagined a new kind of observatory, one that wouldn't collect light, but would instead detect gravitational wave ripples in the very fabric of spacetime. This was a prediction Albert Einstein had made nearly a century earlier, but he himself doubted we could ever build a machine sensitive enough to find them. The idea was audacious, but the concept was breathtakingly simple. This machine would become LIGO, the Laser Interferometer Gravitational Wave Observatory. Construction began on two identical sites, thousands of kilometers apart in the United States, one in the desert of Hanford, Washington, and the other in the forests of Livingston, Louisiana. Why two? To ensure that any signal detected wasn't just a local tremor or a passing truck, but a genuine cosmic event heard by both ears simultaneously. Each LIGO facility is a massive L-shaped structure, with two arms stretching 4 kilometers long. Inside these arms, a near-perfect vacuum is maintained, cleaner than any environment on Earth. Here's how it works. A powerful laser is fired and split into two identical beams. Each beam travels down one of the 4-kilometer arms, bounces off a perfectly polished mirror at the end, and returns to the starting point. Normally, when the two beams recombine, they are perfectly in sync and cancel each other out, resulting in darkness at the detector. But if a gravitational wave from space passes through Earth, it will stretch space-time in one direction and squeeze it in the other. This means one of LIGO's arms will get infinitesimally longer, while the other gets shorter. This tiny change, just for a moment, causes the returning laser beams to fall slightly out of sync. They no longer cancel each other out perfectly. Instead, a flicker of light appears at the detector. That flicker is the signal. It's the fingerprint of a gravitational wave, the whisper of a cosmic cataclysm that happened millions or even billions of years ago. The challenge, however, was monumental. The change LIGO needed to measure was smaller than 1/10,000th the width of a proton. It's the most precise measurement ever attempted by humanity. For years, the team behind LIGO fought an uphill battle against noise. The Earth is a noisy place. Seismic vibrations from distant earthquakes, the rumble of a logging truck miles away, even the gentle waves of the ocean could easily drown out a real signal. The engineers had to invent incredible technology, like advanced suspension systems that isolate the mirrors from the ground, making them the steadiest objects on the planet. For decades, LIGO listened, but all it heard was silence. Funding was precarious. Critics argued the project was a waste of money, and even some of its own scientists began to wonder if they were chasing a ghost. Had they built the most sophisticated machine in history just to listen to nothing? Then, on September 14, 2015, after a major upgrade to its sensitivity, everything changed. At the control room, a signal appeared on the screens. It was clean, loud, and seen at both the Washington and Louisiana detectors, just milliseconds apart. It wasn't noise. It was a faint, rising chirp, not in sound, but in the data. The team was ecstatic, but cautious. They spent months triple-checking every possibility. Was it a hack? A malfunction? A fluke? But the data was undeniable. It was the perfect signature of two massive black holes, spiraling into each other and merging into one. The event had taken place over 1 billion light-years away. Two black holes, each about 30 times the mass of our sun, had been locked in a death spiral. In the final moments before they collided, they were spinning around each other at half the speed of light, warping space-time so violently that the ripples they sent out traveled across the universe. By the time those ripples reached Earth, the distortion they caused was unimaginably small. And yet LIGO had heard it. It was the first direct detection of gravitational waves in history. Einstein's prediction, once a purely theoretical concept, had become a stunning reality. This discovery was so profound, it earned the 2017 Nobel Prize in Physics and opened a new window to the cosmos. But the story didn't end there. The black hole merger was just the first note in a brand new cosmic symphony. In August 2017, LIGO, now working with its European counterpart, Virgo, detected something completely different. This time the signal was longer, lasting for about a minute. The data pointed to the collision of two neutron stars, the incredibly dense, collapsed cores of massive stars that have gone supernova. Neutron stars are city-sized objects so dense that a single teaspoon of their material would weigh billions of tons. Unlike black holes, which swallow everything, including light, the collision of neutron stars was expected to be a brilliant, explosive event, and that's exactly what happened. Just seconds after LIGO and Virgo detected the gravitational waves, gamma-ray telescopes in orbit detected a burst of high-energy light from the same patch of sky. Telescopes all over the world pivoted to look. What they saw was a kilonova, the glowing aftermath of the collision. For the first time in history, astronomers witnessed the same cosmic event in both gravitational waves and in light, from gamma rays to X-rays to visible light and radio waves. This was the birth of multi-messenger astronomy, and it solved one of cosmology's biggest mysteries. Where do heavy elements like gold, platinum, and uranium come from? The universe was born with only hydrogen and helium. Heavier elements are forged in stars, but even supernovas can't explain the abundance of the heaviest ones. The data from this neutron star collision confirmed it. In that single cataclysmic crash, more gold and platinum was created than exists in the entire crust of our planet. The gold in your jewelry, the platinum in your electronics? They were likely forged in the violent collision of two dead stars, long ago and far away. Since those groundbreaking discoveries, LIGO and Virgo have recorded dozens more gravitational wave events. They have built a growing catalog of the invisible universe, charting the mergers of black holes of all sizes and the occasional neutron star collision. Each detection adds a new instrument to this cosmic orchestra we're just beginning to hear. The universe, which we once thought was silent in this domain, is now alive with the sounds of its most extreme events, a symphony of spirals, mergers, and cataclysms. But we're only at the beginning. As incredible as these discoveries are, they represent only the loudest and closest events. What other secrets are hiding in the ripples of space-time? Can we hear the faint hum from the Big Bang itself? Can we detect evidence of cosmic strings or other exotic phenomena predicted by theoretical physics? LIGO is more than just a machine. It's a testament to human curiosity and persistence. It took an audacious dream, decades of work, and unwavering belief to build an instrument that could hear the whispers of the cosmos. And now that we can listen, the universe will never be silent again. Have you ever stood by the ocean, listening to the waves crash, and wondered what secrets the deep holds? That's where we are right now in cosmology. But our ocean is the universe itself, and the waves we read just learning to hear are ripples in the fabric of space and time. Every great scientific discovery isn't an endpoint, it's a doorway. When we first detected gravitational waves, it was a triumph that confirmed a century-old prediction by Einstein. But the real magic wasn't in finding the answer. It was in all the new questions that suddenly became possible to ask. We've opened a new sense, a new way to listen to the cosmos. And what we're hoping to hear next could rewrite everything we think we know. So far, the signals we've picked up with observatories like LIGO are from what we could call the recent cosmic past. Merging black holes, colliding neutron stars, these events happened within the last few billion years. They're like hearing a conversation in the next room. But what if we could hear something from the very beginning of time? What if we could hear the Big Bang itself? It sounds like science fiction, but in theory, it's possible. The first fraction of a second after the Big Bang was a period of unbelievable violence and expansion called cosmic inflation. Space itself stretched faster than the speed of light. And this cataclysmic event should have created a storm of gravitational waves, a primordial hum echoing through the cosmos ever since. Think about what that means. For the first few 100,000 years, the universe was a super-hot, dense plasma, completely opaque. Light couldn't travel through it. It's like a cosmic dark age that our telescopes can't pierce. But gravitational waves would have sailed right through, completely unobstructed. If we could detect them, we would have a direct recording of the universe's birth. It would be the ultimate fossil, a sonic snapshot of creation itself. Right now, these primordial waves are too faint for our current detectors to pick up directly. We're searching for indirect clues in the faint afterglow of the Big Bang, the cosmic microwave background. But scientists are already designing the next generation of observatories, both on Earth and in space, with the sole purpose of hunting for this ancient signal. Finding it wouldn't just be a Nobel Prize-winning discovery, it would be one of the greatest achievements in human history, confirming our origin story in the most profound way imaginable. But the Big Bang is just one of the whispers we're trying to catch. What if the universe is humming with sounds from things we don't even have names for yet? Physics is full of mind-bending theories, and gravitational waves could be the key to proving them. For example, are black holes the weirdest things out there? Maybe not. Some theories predict the existence of even more exotic objects like boson stars. These are hypothetical stars made not of normal matter, but of a strange type of particle. If two of them were to collide, they would produce a gravitational wave signature, completely different from anything we've seen. Detecting such a signal would be like discovering a whole new species in the cosmic zoo. It would prove that the universe builds things in ways our current physics can't fully explain. Then there are cosmic strings. Picture them as incredibly thin, unimaginably dense cracks in the fabric of spacetime, leftovers from the universe's earliest moments. String theory suggests these might exist, stretching across the cosmos. If one of these strings were to snap or vibrate, it would release a powerful burst of gravitational waves. Finding evidence of cosmic strings would be a monumental step toward a theory of everything, uniting the world of the very large with the bizarre rules of quantum mechanics. Even the early universe itself might have made noise. We know that matter can change states like water, turning to ice or steam. Scientists believe the universe went through similar phase transitions as it cooled after the Big Bang. When the fundamental forces of nature split apart, these moments would have been incredibly violent, like the entire cosmos boiling. This cosmic boiling would have sent powerful gravitational waves shuddering through space-time. If we can find the signature of these events, it would be like watching the laws of physics themselves crystallize out of the primordial soup. Each of these possibilities represents a leap into the unknown, a chance to find physics beyond our textbooks. Beyond these exotic ideas, gravitational waves are also helping us solve puzzles that have been bugging astronomers for years. Take black holes. Our detectors have found black holes with masses that just don't fit our models. They re in a mass gap, too heavy to have been formed by a single collapsing star, but not quite supermassive either. Where did they come from? Are they the result of multiple black holes merging over time? Or are they primordial black holes, tiny seeds of darkness forged in the Big Bang that have been growing ever since? By analyzing the waves from their mergers, we can start to piece together their life stories, and in turn, the history of the galaxy. But here's the most tantalizing question of all. Could gravitational waves let us peek inside a black hole? The event horizon is famously the point of no return. According to Einstein, once information crosses it, it's lost to our universe forever. But quantum mechanics disagrees, leading to the famous black hole information paradox. A few fringe theories suggest a fascinating possibility. They predict that after two black holes merge, the new, ringing black hole might produce faint echoes. Gravitational wave signals that bounce off something strange happening at the event horizon, perhaps related to quantum effects. Detecting these echoes would be revolutionary. It would mean the event horizon isn't a one-way door after all. It would tell us that Einstein's theory of gravity is incomplete, and that a new, deeper theory of quantum gravity is waiting to be discovered. We'd be seeing the first hints of how space and time truly work at their most fundamental level. In the end, this is what makes science so exciting. We've spent centuries looking at the universe, mapping the stars with light. Now we can listen to it. We basically just built our first cosmic microphone, and so far we've only recorded a few familiar sounds, the chirps of black holes. But a whole symphony is playing out there. There are crescendos from cosmic phase transitions, bass notes from strange new objects, and maybe, just maybe, a faint ancient hum from the dawn of time itself. We don't know what we'll find. Most of the universe's song is still a mystery. But for the first time in history, we're able to listen. And every new signal, every strange vibration, reminds us that the grandest discoveries are still ahead of us, waiting in the silence. For thousands of years, humanity has looked up at the night sky and seen light. From the earliest stargazers to the most powerful telescopes, Our entire understanding of the universe has been built on what we can see. We built sharper and sharper eyes first, with glass lenses, then with cameras that could detect radio waves, X-rays, and gamma rays. Each new window revealed a different, stunning layer of the cosmos. But here's the thing about light. It has its limits. Some cosmic events are so extreme, so violent, that light is either completely swallowed up or never even created. Imagine two black holes silently spiraling toward each other in the dark. To our telescopes, that's just an empty patch of space. Until recently, these cosmic giants were completely invisible, their dramatic lives unfolding beyond our reach. But what if we could listen to the universe, instead of just looking at it? What if we could hear the thunder of cosmic collisions across billions of light years? It's not science fiction anymore. It's the reality of gravitational waves. For the first time in human history, we have a new sense to explore the cosmos. We can now hear what the universe is doing, even when it's completely dark to our eyes. Let's talk about those invisible giants, black holes. By their very definition, they trap all light. They are cosmic voids. But when two of them collide, the event is anything but quiet. The fabric of spacetime itself rings like a drum, sending out ripples across the universe. These ripples are gravitational waves. Before we had detectors like LIGO and Virgo, these monumental mergers would have happened without us ever knowing. Now, detecting them is becoming almost routine, finally listening to the secret lives of black holes. And it's not just black holes. Neutron stars, the super-dense remnants of massive stars, also tell their hidden stories through these waves. When two neutron stars spiral in and collide, they create an event so powerful it forges heavy elements like gold and platinum. These collisions produce a flash of light, a kilonova, but the gravitational wave signal often arrives first. It's like a cosmic heads-up call. It's telling astronomers exactly where to point their telescopes to witness something extraordinary about to unfold. This combination of hearing the event with gravitational waves and then seeing the afterglow with telescopes is a complete game changer. It's like watching a movie with both sound and picture. The sound tells you the raw power and dynamics of the collision, while the visuals show you the spectacular aftermath. Together, they allow scientists to reconstruct these cosmic events with a level of detail we could only dream of before. We can now piece together the story of dying stars from start to finish. Every gravitational wave that we detect on Earth is more than just a scientific curiosity. It's a new data point on a revolutionary cosmic map. We're charting the invisible universe. These detections pinpoint where massive black holes are lurking, even in the darkest, most crowded regions of galaxies. They're telling us how often stars collapse, merge, and die, giving us a census of the most extreme events in the cosmos. But perhaps one of the most powerful things they do is give us a new cosmic ruler. Gravitational waves provide a completely independent way to measure distances across the universe. Why does that matter? Right now in cosmology, there's a big debate. We have two main methods for measuring how fast the universe is expanding. It's known as the Hubble constantan. They give us slightly different answers. It's a major puzzle. Gravitational waves offer a brand new way to measure this expansion. And they might just be the key to solving this cosmic tension and understanding the ultimate fate of our universe. You might be thinking this is all fascinating, but what does it have to do with me here on Earth? The answer is a lot. The incredible challenge of detecting gravitational waves has pushed our technology to its absolute limits. To measure a ripple in space-time that's smaller than the width of a proton, scientists had to invent unbelievably stable lasers. Vibration dampening systems that can isolate an instrument from a nearby footstep, and quantum optics techniques that seem like magic. These breakthroughs aren't just for astronomy. They have real-world applications in fields like precision engineering, medical imaging, and even resource exploration. The technology developed for LIGO is already inspiring innovations that will shape our future here on Earth. The quest to listen to the whispers of the cosmos has made us better engineers and inventors. But beyond all the science and technology, there's something more profound. Gravitational waves give us perspective. On our little blue planet, our daily struggles, our triumphs, and our conflicts can feel all-encompassing. They can feel like the most important things in the universe. And then, a signal arrives. A faint whisper that has traveled for 1 billion years from the collision of two black holes, each dozens of times more massive than our sun. In that single moment of detection, we are reminded of our true place in the cosmos. We are tiny beings on a tiny planet, yet we have built instruments sensitive enough to hear the echoes of creation. It's a humbling and awe-inspiring thought. This is more than just a new tool for science. The discovery of gravitational waves represents a fundamental shift in human consciousness. For our entire existence, we have been cosmic observers, limited to what we can see.
Ow!
We are cosmic listeners.
Ow!
We are tuning into the very fabric of reality, hearing the symphony that has been playing all along. Unheard. It connects us to the universe in a way we've never been connected before. It reminds us that our planet isn't an isolated island, but an integral part of a grand, dynamic cosmic drama playing out across the vast expanse of space-time. From our perspective here on Earth, gravitational waves are not just some abstract ripples in a faraway dimension. They are the voice of the universe. And finally, after all this time, we are learning to listen. For centuries, humanity has gazed at the stars, using light to paint a picture of the cosmos. But what if there was another way to experience the universe? A way to feel its most violent and energetic events, not by seeing them, but by hearing the very fabric of space-time ripple? This isn't science fiction. This is the story of gravitational waves, and how a group of determined scientists built the ears of the universe. The journey begins not with a bang, but with a whisper of an idea. In the mid-20th century, physicists wondered if Albert Einstein's prediction of ripples in space-time could ever be proven. The first real attempt came in the 1960s from a physicist named Joseph Weber. He built massive aluminum cylinders, hoping they would ring like a bell when a gravitational wave passed through. It was a bold, almost audacious idea. While his bar detectors ultimately didn't find anything, they lit a fire. It proved that the question was worth asking. Weber planted the seed. If the universe could tremble, humanity should try to listen. By the 1970s, a new generation of visionaries emerged. Physicists like Rainer Weiss at MIT, Kip Thorne at Caltech, and Ronald Drever, also at Caltech, began to dream bigger. They imagined an observatory unlike any other. Instead of a metal bar, they envisioned using lasers. The concept was elegant in its simplicity, yet staggering in its ambition. It was called laser interferometry. The plan was to split a single laser beam into two, send each one down a very long perpendicular tunnel, and then bounce them off mirrors to recombine them. If the two beams returned perfectly in sync, nothing had happened. But if a gravitational wave passed by, it would stretch one tunnel while squeezing the other, knocking the light beams out of phase. This tiny, almost imperceptible shift would be the signal. It was a brilliant idea on paper, but in reality, it seemed nearly impossible. To succeed, they would need to measure a distortion smaller than the width of a single proton. Think about that for a second. It's like trying to measure the distance to the nearest star with the accuracy of a single human hair. When they presented this idea to funding agencies, the skepticism was palpable. Critics called it too ambitious, too expensive, a fantasy. For years, Weiss, Thorne, and Drever fought an uphill battle. They spent countless hours refining their designs, running simulations, and pleading for resources, all while many in the scientific community dismissed their dream as a fool's errand. But they refused to give up. They believed that humanity deserved to hear the universe's hidden symphony. Finally, after decades of persistence, their vision got the green light. In the 1990s, the United States National Science Foundation approved the construction of Litho Laser Interferometer Gravitational Wave Observatory. This wasn't just one facility, but two, built 3,000 kilometers apart. One in the deserts of Hanford, Washington, and the other in the forests of Livingston, Louisiana. Having two detectors was crucial to rule out local disturbances like earthquakes or even passing trucks, ensuring that any signal they found was truly cosmic. The engineering required for LIGO was on a scale never attempted before. Each facility featured two 4-kilometer-long vacuum tunnels, forming a giant L. These are some of the largest and emptiest vacuum chambers on Earth, with an air pressure 1/trillionth that of our atmosphere. Inside, the mirrors were polished to near-atomic perfection and suspended by a complex system of pendulums and dampeners to isolate them from any earthly vibration. The laser systems were engineered to be so stable that they could detect that mind-bogglingly small shift, 1/10,000th the width of a proton. It was a monument to precision, a machine built at the very edge of what was technologically possible. After years of construction, the initial version of LIGO began listening in the early 2000s. For nearly a decade, it ran in near silence. It listened and listened, and heard nothing. The silence was deafening. The old doubts began to creep back in. Had they built this colossal billion-dollar machine for nothing? Had the critics been right all along? The hundreds of scientists and engineers who had dedicated their careers to the project? It was a trying time, but their belief never wavered. They knew they just needed a more sensitive instrument, so they went back to the drawing board. With another round of funding, the team began a massive upgrade. The result was Advanced LIGO, a new and improved version that was 10 times more sensitive than its predecessor. This meant it could survey a volume of space 1,000 times larger. The upgrades were completed in 2015, and the new, improved ears of the universe were switched on. The team held its breath. Would this finally be it? And then, it happened. On September 14, 2015, just days after Advanced LIGO began its first observing run, a signal arrived. It was a faint chirp, lasting less than a second, that swept up in frequency. The data poured into the control rooms at both Hanford and Livingston. The signal was identical in both detectors, separated only by the few milliseconds it took for the wave to travel between them. It was unmistakable. This was not a fluke. It wasn't a truck or an earthquake. It was a gravitational wave. For the first time in history, humanity had directly detected a ripple in the fabric of spacetime. The source? Its black holes? Each about 30 times the mass of our sun, spiraling into each other and merging in a cataclysmic collision over 1 billion light-years away. When the news was announced to the world, it wasn't just a scientific breakthrough, it was a profoundly human moment. It was the culmination of a century-old prediction and the reward for 50 years of relentless, often thankless work. But LIGO doesn't listen alone. Across the Atlantic, near Pisa, Italy, the Virgo detector adds another crucial ear to this cosmic network. Virgo's collaboration with LIGO proved its immense value in 2017. Together, they detected the collision of 2 neutron stars, because there were 3 detectors listening instead of 2. Astronomers could triangulate the source's position in the sky with incredible precision. Telescopes all over the world were able to point to that exact spot and witness the afterglow of the collision at kilonova for the first time. This single event launched a new era of multi-messenger astronomy, where we can both hear and see the same cosmic event unfold. And the global effort doesn't stop there. In Japan, the KAGRA detector is pushing the technological frontier even further. Built deep inside a mountain to shield it from seismic noise, KAGRA uses cryogenically cooled mirrors to reduce thermal vibrations. Each new observatory that joins the network sharpens our collective hearing, allowing us to pinpoint sources more accurately and detect even fainter whispers from the cosmos. This isn't just one country's project, it's a global pursuit, a testament to what international cooperation can achieve. Behind these incredible machines and groundbreaking discoveries lies an enormous human cost. Imagine dedicating your entire career to building an instrument with no guarantee it would ever work. Years, even decades, spent troubleshooting, refining, and fighting for a dream that might never be realized. This is the story of countless scientists and engineers who poured their lives into LIGO and its partner projects. But the reward, when it finally came, was immeasurable. That first chirp in 2015 justified all of it. It was the moment humanity expanded its senses beyond light, sound, and touch. We had built a new sense for ourselves, the ability to feel the universe tremble. What makes these observatories so unique is that they are more than just instruments. They're infrastructures of patience. These massive silent machines sit and listen day in and day out, waiting for the rare moments when the cosmos sends a message. Each detection is a powerful reminder that science isn't always about sudden flashes of genius. More often, it's about persistence. It's about the quiet, decades-long work that suddenly pays off with a discovery that rewrites our understanding of reality. Through these incredible ears we have built, the human gaze now stretches beyond light itself. We have learned to listen to the silent symphony of the universe. Ever since humanity first looked up at the stars, we've been defined by what we can see. But what if I told you that our eyes have been missing most of the story? What if the universe has a voice, and we've only just learned how to listen? In 2015, something incredible happened. Deep underground in an L-shaped tunnel, a set of incredibly sensitive instruments twitched. It was a signal so faint it could barely be measured, a ripple in the fabric of spacetime itself. This was LIGO, the Laser Interferometer Gravitational Wave Observatory. And it had just detected the collision of two black holes, a billion light-years away. For the first time, we didn't just see the cosmos, we heard it. Think of it like this. For centuries, we've been watching a silent movie. Galileo's first telescope was like turning the film on. We saw planets, stars, and entire galaxies. But that 2015 detection? That was like someone finally plugging in the sound. That first faint chirp was just the beginning of a cosmic symphony. The story of science is one of constant refinement. Galileo's first telescope was a crude tube with a couple of lenses, yet it completely rewrote our map of the heavens. It showed us we weren't the center of everything. Today, LIGO and its partner observatories are like that first telescope. They're groundbreaking, but they have their limits. Here on Earth, our planet is well noisy. Cars, earthquakes, even the wind and waves create vibrations that can drown out the faintest cosmic whispers. It's like trying to hear a pin drop during a rock concert. So, what's the next step? How do we get away from all this noise? Simple. We leave. We take the observatory to the one place that's truly quiet. Space. Enter LISA, the Laser Interferometer Space Antenna. This isn't just another space telescope. It's one of the most ambitious science missions ever conceived. Forget detectors a few kilometers long. LISA will be a constellation of 3 spacecraft flying in a perfect triangle, millions of kilometers apart. These spacecraft will orbit the Sun, trailing behind Earth, linked by laser beams, more precise than anything we've ever built. This immense scale changes the kind of music LISA can hear. If LIGO detects the high-frequency chirps of smaller black holes and neutron stars colliding, think of LISA as the universe's subwoofer. It's built to listen for the deep, rumbling bass notes of the cosmos. What kind of events produce these cosmic bass lines? We're talking about the titans. Supermassive black holes, millions or even billions of times the mass of our Sun, spiraling into each other at the hearts of merging galaxies. These are events of unimaginable violence, shaking space-time on a scale we can barely comprehend. LISA will hear their final, slow, powerful dance. It will also listen for something called extreme mass ratio in spirals. Picture a small, stellar mass black hole caught in the gravitational grip of a supermassive giant. It will orbit that giant for thousands, maybe millions of years, getting closer and closer, tracing an intricate path through space-time before it's finally swallowed. Each orbit sends out a steady pulse of gravitational waves, continuous hum that maps the warped geometry around the giant black hole with incredible detail. It's like sending a tiny probe into one of the most extreme environments in the universe. But the most tantalizing sound LISA might hear is the oldest of all. A faint, persistent hum from the very beginning of time. Cosmologists believe that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-fast expansion called inflation. This cataclysmic event should have flooded the infant cosmos with gravitational waves. These primordial waves would still be echoing through space today, a relic of creation itself. No telescope, no matter how powerful, can see this far back. Light couldn't travel freely until hundreds of thousands of years after the Big Bang, but gravitational waves could. If LISA detects this primordial hum, it would be like hearing the echo of creation, the soundtrack of the Big Bang. So, with instruments like LIGO on the ground and LISA in space, we're assembling a cosmic orchestra. Each gravitational wave that we detect is more than just a signal. It's a message, a piece of a puzzle. It carries a wealth of information about its source. The masses of the objects involved, how fast they were spinning, and how they merged. It's a birth certificate for some of the most violent events in the universe. By collecting enough of these signals, we can start to create a completely new map of the universe. Not a map of light, but a map of gravity, map of the invisible. We can finally start to answer some of the biggest questions we have. How did the supermassive black holes at the center of galaxies like our own get so big?
Ow!
Are they built from countless smaller mergers?
How often?
Do neutron stars, the dead cores of massive stars, collide? We know these collisions forge heavy elements like gold and platinum. By listening to them, we can literally count how much of the universe's treasure is created this way. And of course, there's that ultimate prize, the sound of the Big Bang. Confirming the hum of inflation would be one of the greatest scientific discoveries of all time, giving us direct evidence of how our universe began. This isn't just astronomy anymore. This is cosmic archaeology. We're not just observing things, we're decoding the history of reality itself, written in the vibrations of spacetime. This all sounds very grand, very cosmic. But why should it matter to us, here on our little blue planet? What does the sound of two black holes merging 1 billion years ago have to do with our daily lives? Everything. It's because every time we find a new way to perceive the universe, it fundamentally changes our perception of ourselves. When we learned that the Earth revolved around the sun, it wasn't just an astronomical fact. It shifted our philosophy, our art, our sense of place. When we discovered galaxies beyond our own Milky Way, our sense of scale was shattered and rebuilt, grander than before. We realized our home was just one island in an endless cosmic ocean. Now we are learning to hear. This new sense reminds us of our fragility, floating on a tiny rock in a universe that shakes and trembles with unimaginable power. But it also reminds us of our incredible potential. A species that evolved on one small world has managed to build instruments that can listen to the echoes of creation. We are no longer just passive observers looking up at a silent sky. We are active participants in a grand cosmic investigation. We are tuning our instruments, leaning in, and listening. Future generations, perhaps even future civilizations, might look back at this moment in the early 21st century as a turning point. The moment when humanity grew a new sense. The moment we stopped just looking at the universe and finally learned to listen to its story. Thanks for joining me on this journey into the sound of the cosmos. If you enjoyed this, please consider liking the video and subscribing to the channel for more explorations into the frontiers of science. We've got so much more to discover together.